I want to focus on what I call the ML lifecycle. What do I mean by the lifecycle? Typically, when you take any application that you're trying to embed in machine learning, there's a certain process that you have to go through from the beginning in terms of collecting the data to be able to train the model before you can actually deploy it. Having that big picture is extremely important because it allows us to understand how much effort needs to be put in at various stages. Typically, when you take a machine learning course, you end up focusing heavily on the neural network. You try to understand what is my input data? What is my output from the neural network? How do I do inference? And mostly, how do I end up training the network? All of this is a very small portion of a big puzzle of deploying machine learning in the field. It's important you keep in mind because this is just a machine learning code box. This code box is a small portion of what it takes to build a full-on TinyML application. The boxes that I'm showing you here are common to all kinds of machine learning pipelines. The size gives you a rough idea of how much effort and time is required relative to just building the machine learning code box. I'm telling you this so you know where you will need to put in effort when you're building a production system and why it's actually worth it. So this whole thing boils down to having an AI infrastructure. An AI infrastructure includes the components that support AI, as well as non-AI components such as the data centers and the developer operations once the system is rolled out. To build any application successfully, you need to have a vertical introspection of this whole pipeline. So the first element of the AI infrastructure is data engineering. We're going to be doing data engineering quite a bit, in fact, in this course across all three sensors, all three applications. And we will also try to understand what are the nuances in data engineering to capture data, to clean the data, to modify its format so it's ready to input in the neural network. Then we'll talk about model engineering. Model engineering is all about building a model where you will iterate till you have the right structure to meet the requirements. You'll evaluate the model in terms of how well does the model generalize? What is its accuracy? How sensitive is it? And so on across a relevant set of metrics. So you will be able to tell how well this satisfies the application requirements. And then there's a model deployment, where you will take the model that you have trained to check how well it fits for deploying. You will learn methods to adjust models to fit constraints in the resources, and then you will convert it so it runs efficiently on the target hardware. And of course, finally, once you've deployed it, you end up doing product analytics, where you tend to have dashboards where you are constantly monitoring how the machine learning system is actually performing in the field. And then you circle back to the top. This is typically how it works. There are 4 fundamental building blocks, I would say, in any AI infrastructure system. I want you to keep this in mind because I'm going to step through each one of these now. What is data engineering? Data engineering, as you try and build any tiny application, is all about defining what are the data requirements. If you want to be able to say, oh, okay, Google, or what are the data requirements there? Is it simply about, I need to be able to detect those 2 words and that's it? Or are there many more nuances to that? For instance, you need to think about what does the data need to look like in a noisy environment versus a very clean, quiet house that you're actually collecting the data to train the model from. You've probably never thought of that, huh? And then you need to go about the process of actually collecting the data. Where do you get the data from? You and I are going to stand in front of a microphone and keep saying, okay, Google, okay, Google, okay, Google, okay, Google, okay, Google. Well, that's still a male voice, right? So no matter how you do it, you've got to systematically think about where your data is going to come from. The scale, the quality, the features, all of those nuances are actually going to matter quite a bit. And we'll be looking into that much deeper. Then you've got to go about the process of actually collecting the data. Where are you going to get this data from? Are you and I going to keep doing this manually? And so on, right? So then you go through the process of actually labeling the data. And so your network knows how to actually learn from that data. And then you've got to make sure you actually clean the data that you've got, because not all data is really good. Because sometimes the mic doesn't work. Like, I wasn't actually saying anything, but that actually happens in the real world. And so you've got to make sure that you actually clean the data. Then, of course, you've got to train the data. And then you've got to prep the data and pre-process it in a way that's actually ready to be fed into the neural network models. Remember, we learned about data augmentation, right? For images where you could skew, rotate, shift, and manipulate the inputs, and doing all of that without collecting additional data. So that's part of data engineering. And we'll be doing that for all three application use cases over here. And then, of course, you tend to repeat the cycle because machine learning is all about data, and you've got to go and get more data, and you've got to repeat the process over and over again. Then let's look at model engineering. You've got to train the machine learning model, and you've got to improve the training speed. We'll look at transfer learning, for instance, where you, instead of starting from training the model from scratch, you take a pre-trained model, and then you make subtle tweaks in order to accelerate its ability to train much faster. Then you've got to define the right set of metrics. What is a good accuracy metric? It depends on the application use case. Well, are there too many false positives or too many false negatives? So you've got to try to understand the application use case. And then you've got to repeat the cycle in terms of optimizing the model training in order to get that model to be able to meet our metric requirements. And if you're a model engineer, typically you've got to keep up with the state of the art, which means reading a lot of literature. That's the job of a machine learning engineer. It's not only about building stuff. You've actually got to know the field really well. And we'll try to give you a bit of sampling and help you read some papers and understand where key changes or seminal works happened along the way. And I want to make sure that you're a practical engineer when you get out of this program. And the third step is model deployment. And you'll physically put the model on an embedded system, which we'll be doing in part 3. So you'll need to understand how to take a TensorFlow model and convert it into a format and a size that can actually fit on a tiny device. We'll learn about what makes efficient model conversion in terms of size, speed, energy. And then you've got to evaluate its performance capabilities. Does it meet the real-time requirement you need? If I say, hey, Siri, and then it takes like 3 seconds, how do we optimize for latency versus model size? Then you're putting these things onto a small microcontroller running on a battery. So you've got to be very conscious about energy. And what does that mean in terms of optimizing for performance? Might not actually give you the best energy efficiency. And then there's the aspect of security and privacy, where you're deploying these models. Well, what data is this thing actually collecting while it's running? Is the data being kept safe or not? And so we've got to engineer that system accordingly. Then, of course, you're performing inference using some sort of APIs. And you've got to know how restrictive they are across different hardware platforms. And then you finally might want to do some on-device fine-tuning of the model. But even after you put the trained model on the device and you send it out into the market or deploy it across thousands of devices, you want to do some sort of online learning and keep updating the model so it adapts to the changing application settings. And once a system has been deployed, while to thousands of customers, you'll need to know how well it's been working across different customers. So you do product analytics, where you build dashboards that allow you to visualize the operational data and evaluate the performance across deployment cohorts. And then you try and figure out what's the value add, that the ML application deployment is actually giving the customers or the end users. And finally, you try to repeat this cycle so you can actually get advancements and improvements. And we've got to be focusing on this vertical stack in TinyML. It's extremely important. It might seem non-technical at this point in time. I want you to keep these concepts in mind because later on, as we go in, we're going to focus on the exact mechanics, right? How do you do data engineering for keyword spotting? How do you do data engineering for anomaly detection? How do you do data engineering for vision-based pipelines? And similarly for model engineering and model deployment and so forth. Now, by and large, because we are not building a product, we are actually going to ship out to the market. The focus is going to be on the top 3 bars: data engineering, and model deployment. And with that said, let me walk you through the full cycle of the machine learning lifecycle. It starts with data collection being the first critical step. Then we're going to go on to doing some data pre-processing. And after that, we're going to have to see if the data is actually good enough, or do we need to go back and collect more data? If the data is good enough, then we're going to start doing some labeling on it. Say it's a cat and a dog or whatever it is, putting bounding boxes in the right places. Once you get that, you're going to prep the data to actually be ready to go in and do some training in the process pipeline. And once you do that, we start the training of the networks and we start evaluating whether the models are actually performing well, given the metrics we have defined. And you learned about that with validation sets and test sets. And then we're going to start thinking about how do we actually deploy this model in the real world. And once we deploy it, we get analytics and we continue this sort of circle over and over again. And this is a typical life cycle of a machine learning system. And we will go through most of these phases for every one of the applications because there are subtle differences that you can actually have a deep appreciation for. And with that said, I hope you keep this in mind as you go through in deeper aspects of each of these boxes. And whenever you feel lost, if you want to come back and look up this life cycle and say, oh, that's right, I'm spending time in this particular box, and this is why it's important. And if any one of these steps is a weak link, the whole system will fail. Because if your data is poor right at the beginning, you're going to do all this hard work to deploy it when the machine is actually not going to be doing its inferences right. It's garbage in, garbage out. For instance, if the keyword spotting is supposed to work for my mom, but it doesn't, why? Because, well, the model was not trained well for Indian accents specifically. And then now if I try and buy all these devices, put it around the house for my mom, well, too bad. None of them are really going to work well. So even if I have a fancy device, which works for me, doesn't work well for her because the model didn't have her kind of data. So that has serious implications as we get into more life-critical applications down the line. And with that said, in this lecture, we're going to focus on one of the critical pipelines for every single application, which I will then call the machine learning workflow. I'll see you soon.